Okay, so this is our fifth problem of optimization. If you look at the problem sheet on optimization, this is problem number 20. So let's read the problem. Two posts, one 3 meters high and the other 12 meters high, stand 5 meters apart. They are to be stayed by two wires attached to a single stake, running from ground level to the top of each post. Where should the stake be placed in order to use the shortest amount of wire? Obviously here, since we're asking for the shortest amount of wire, we will try and minimize the length of wire used. Well, let's visualize the situation. We have a 3-meter post. There's the ground, and there is a 12-meter post. Obviously my picture is not up to scale. That doesn't matter. So this is 3. This is a constant. This is 12, also a constant. And the poles, this one and this one, are 5 meters apart. So the length of this segment is 5. And now we're staying the two posts with a wire that is stayed at the ground. So if you think of it, you say, well, we'll have a stake here. Suppose it's here. And then you're going to tie up a wire from the top of this pole down to our stake. And then we'll tie up a wire from the top of the other pole down to that very same stake. And the question is, well, where do we position our stake so that the amount of wire used is minimized? We want the shortest amount of wire. Well, call this segment X. We don't know where to position our stake, so it's an unknown. So this is, say, X. And since the total length is 5, this is 5 minus X. And now, well, two things. First, what is our function? Well, if you notice, we have two right triangles. And the function is the length of this plus the length of this, the total length of wire used. We have two right triangles, and you notice that the length of this piece of wire is just the hypotenuse of the smaller right triangle. The length of this piece of wire is the hypotenuse of this larger right triangle. So our function from Pythagoras' theorem, well, this would be the square root of 3 squared plus x squared. So the root of, if you prefer, x squared plus 3 squared, but 3 squared is simply 9, plus the length of this wire. Well, again, this is the square root of the base squared, 5 minus x squared, plus 12 squared. 12 squared is 144, plus 5 minus x squared. And so we have now our target function. We will try and minimize this function. What is the possible range of x values, right? Our goal will be to minimize this function of x. What is our interval? Well, if you think of it, could x be negative? If x were negative, this would be x equals 0. This would be a negative value of x. If x is negative, you see that the length of the first wire is the same, right? If you take this value and you have it negative, it's a reflection. You get the exact same triangle. So the length of the first piece of the wire is the same. And then obviously, the length of the second wire will be much longer because you'll go from this wire to, if the value of x is negative, this one. So clearly, we will not obtain a minimum amount of wire, the shortest amount of wire possible, if we allow x to be negative. And if you think of it, x could go up to 5. Could we possibly attain a minimum value if x is bigger than 5? Well, it's the same argument, right? If x, now you reflect about this point, it ends up here. And so the length of the longer piece of wire is the same. But now the length of this segment is much longer. It would be something like this. So clearly a minimum value for the total length of wire cannot be achieved if either x is negative or bigger than 5. So our interval for x values ranges from 0 to 5. And this is great because if you notice, we have two square roots. We're adding them up. It's a sum of squares. So we will never have negative values inside of the square roots. The two are polynomials. The square root over the positive real axis is continuous. So our function f of x is continuous. And so we have a continuous function on a closed and bounded interval. So we know that to maximize and minimize this function over a closed and bounded interval, we simply have to evaluate the function at the left-hand point of the interval, the right-hand point, and at the critical points inside of the interval. So all we have to do now is find the critical points of our function. So let's differentiate. This is, think of it as a power of 1/2. So we use the chain rule, differentiate the power of 1/2. And so we get 1/2 x squared plus 9 to the 1/2 minus a half, negative 1/2. But that's just the derivative of the square root, times, by the chain rule, the derivative of the argument, which is 2x, plus the derivative of the second function. Once again, the square root is a power of 1/2. It is the outside function, so by the power rule we get 1/2, 144, plus 5 minus x squared, 1/2 minus 1, negative 1/2, times, by the chain rule, the derivative of the argument. The derivative of this by the chain rule again will be 2 times 5 minus x. Chain rule times the derivative of 5 minus x, which is negative 1. We now have our derivative. Let's simplify, and then we'll be able to find our critical points. 2 over 2 is 1. 2 over 2 is 1. I will send this down. It will become a positive 1/2 power. And I'll replace the 1/2 power by a square root. So I end up with x over the square root of x squared plus 9. Then what? Well, I'll also send this down, so it will become a positive 1/2 power, which will be a square root. And I'll be left on top with negative of 5 minus x. So negative over the square root of 144 plus 5 minus x all squared. And now we have our derivative. Again, critical points are points where the derivative may be 0 or undefined. The only way where f prime may be undefined is if we had a division by 0, but we have the root of a sum of squares. So this is always at least 9, always at least 144. We will never have a division by 0, so f prime is always defined. Then we have to find values of x where the derivative may be equal to 0. Well, let's put these over a common denominator. So we are going to have x times this minus this times 5 minus x. I'm just cross multiplying this times this minus this times this. So minus 5 minus x times the square root of x squared plus 9 all over the square root of x squared plus 9 times the square root of 144 plus 5 minus x all squared. And now we have our derivative as a single fraction. And why did I do this? Well, the derivative will be equal to 0. We're looking for our critical points. And of course, if a fraction is equal to 0, the only way for this to be possible is if the numerator is equal to 0. So, this minus this equals 0. I will send this on the other side. And I'll have that x times the root of this equals 5 minus x, the root of x squared, plus 9. I'm sending this on the other side. The negative becomes a positive. So 5 minus x, the root of x squared, plus 9. And now we're trying to solve for x. This does not seem like an easy equation to solve for, namely because of the square roots. The idea is, well, why not square both sides? If this equals this, then the square of this equals the square of this. And by squaring both sides, we will eliminate the square roots. So let's square both sides. If you square x, you get x squared. If you square the square root, it goes away. And you have x squared times the argument, so it'll be x squared if you distribute, times 144. Plus x squared times this, so x squared times 5 minus x all squared equals, now the right hand side you'll have 5 minus x all squared, square the square root, it goes away, and so if you distribute you'll have this squared times x squared plus this squared times 9. So plus 9 times 5 minus x all squared. And if you look at this, there is something interesting. X squared times 5 minus x squared times 5 minus x squared. So this term shows up on both sides of the equality. We can cancel it. And so we're left with a now much simpler equality. We have 144 x squared equals 9 5 minus x squared. Let's try and see if we can cancel common factors between 9 and 144. 144 is 12 times 12, but 12 is 3 times 4. So we have 3 times 4 times 3 times 4. It is 9 times 16. So we have 9x squared. Well, 144 is 9 times 16, so times 16 equals 9 times 5 minus x squared. You can cancel a 9, and so you're left with, quite simply, 16x squared equals 5 minus x squared. And if you look at this, this is a simple quadratic. Let's expand this out, send it on the other side, and hopefully we'll be able to factor. If you look at squaring this, you'll get 5 times 5, 25. 5 times negative x, negative 5x, but twice of that, negative 10x. Negative x times itself is positive x squared. And so now, send this on the other side, and you'll have 16x squared minus x squared. This is 15x squared. Negative 10x will become positive 10x. positive 25 will become negative 25, and this is equal to 0. And so we have reduced finding our critical points to solving this quadratic equation. And now you say, well, okay, as always, you could fall back on the quadratic formula, but can we do simpler? Can we try and factor by inspection? Because of the 15 here, it's not clear how this will factor, but if you notice, we can make our life a little easier. Every term is a multiple of 5. So we can factor a 5, and we'll be left with 3x squared plus 2x minus 5 equals 0. So of course, if 5 times something is 0, this must be 0. And now it might be easier to see how to factor this quadratic, right? If you don't see a factor, remember the result. If you have a value of x, say a, where f of a is 0, you have a free factor in x minus a. Look at the coefficients. 3, 2, and 5. 3 plus 2 is 5. So if you set x to be equal to 1, you'll have 3 times 1, 3, plus 2 times 1, 2, 3 plus 2, 5, minus 5 is 0. So this quadratic polynomial is 0 when x is 1, so automatically x minus 1 is a factor of this polynomial. Let's find the other factor by long division. And now we're almost done. So we will divide 3x squared plus 2x minus 5 by the now found free factor of x minus 1. So 3x squared minus 3x. X squared minus 3x squared is 0. 2x negative 3x is 2x plus 3x, which is 5x, minus 5. Minus 5 minus 0, negative 5, plus 5, 5x minus 5, which gives us 0. So now we have a complete factorization of our quadratic polynomial. We were looking for 3x squared plus 2x minus 5 being equal to 0. But this factors as x minus 1 times 3x plus 5. Well, if you have a product of two numbers, the result being 0, at least one of them must be equal to 0. So x minus 1 could be 0, therefore x equals 1 is our first critical point. Or 3x plus 5 could be 0, but if you solve for x, you'll have x as negative 5 over 3. So these are the two critical points of our function, but if you remember, the range of x values were only allowed from 0 to 5. So x equals 1 is a critical point inside the interval, so we must check the value of the function at 1. Negative 5 over 3 is outside, and so we don't care about this critical point. It cannot yield a minimum. And now we're good to go. We have our two endpoints, 0 and 5, and the single critical point inside the interval, so we only have to evaluate the function at these 3 points. Let's recall our function, f of x, which was the root of x squared plus 9, plus the root of 144 plus 5 minus x all squared. And now we are going to evaluate our function at 0, 5, and 1. And let's see where we can find our minimum value for f, therefore minimizing the length of wire used. Alright, so the value of f at the left-hand point when x is 0. If you plug in x equals 0, you have the root of 9, which is 3. 5 minus 0 is 5. 5 squared is 25. 144 plus 25 is 169, which is 13 squared. And so the root of 169 is 13. 13 plus 9 is 16. So if x is 0, we have to use 16 meters of wire to stay these two poles. Let's look at the function at the right-hand point, 5. What do we have here? Well, 5 squared is 25, plus 9 is 34, so it's the root of 34, plus, if x is 5, 5 minus 5 is 0, and the root of 144 is just 12, so it's the amount of wire used is root of 34 plus 12. If you use your calculator, you'll find this is approximately 17.83 meters, so longer than when x were 0. And finally, let's evaluate the function at the critical point, x equals 1. Now what is f of 1? Well, plug in 1 in here, you get root of 1 plus 9 root of 10, plus 5 minus 1 is 4, 4 squared is 16, 144 plus 16 gives you 160. So it's the root of 160. And if you use your calculator, you will find that the root of 10 plus the root of 160 is approximately 15.81. So now we have the values of our function f at the two endpoints of the interval and at the only critical point inside of the interval. So we know that one of these values must be the maximum and one of these values must be the minimum. Well, obviously, this is the maximum value, right? 16, 17.83, 15.81. So if we take x to be 5, we will end up using the maximum amount of wire, roughly 17.83 meters. But we were trying to stay these two posts using the least amount of wire possible. And so we look for the minimum value, which happens when x equals 1. So this is our minimum value. And it occurs at the absolute or global minimum of x equals 1. And we're done. So if we draw the picture, you have your two posts. One is 3 meters high, the other 12 meters high. And this was 5 meters. And we know that the stake should be placed, x was 1. And recall your picture that x was the distance from the shorter post. So we have to plant our stake 1 meter away from the shorter post, therefore 4 meters away from the longer post. And this way, by tying up the wire from the top of the two posts down to the stake, we will use the shortest amount of wire possible in the amount of 15.81 meters. And this is our conclusion.